Look under the hood of almost any modern electric vehicle, and you will find a permanent magnet synchronous motor. Manufacturers rely on this specific design because it delivers high power density in a compact package. To generate that torque, the motor requires permanent magnets made from rare earth elements like neodymium and dysprosium, any foreign product containing Chinese rare earth content. In response, governments are trying to build their own processing infrastructure from scratch. India, for example, just launched a 7,280 crore rupee subsidy scheme to kickstart domestic rare earth magnet manufacturing. This leaves automakers with a difficult choice. They can either invest billions in rebuilding a toxic extraction and processing pipeline locally, or they can re-engineer their motors to operate without physical magnets. To bypass the risk, the industry is splitting into three distinct engineering paths. As the flowchart shows, manufacturers are attempting to swap out the magnet materials, alter the mechanical architecture, or replace the physical magnets with software-controlled fields. Every path away from rare earths involves a technical trade-off. There is no solution that offers a free lunch. Automakers simply have to decide which performance penalty they are willing to absorb. The first option is the material swap, changing the magnet's chemical makeup. This scorecard evaluates range, manufacturing, and supply risk. Swapping in ferrite scores well on low supply risk, but it flashes red for driving range and efficiency. The physical trade-off is steep. It is like replacing gold with aluminum. Because ferrite is a mathematically weaker magnetic material, engineers have to build the motor significantly larger and heavier just to match the power output of a rare earth motor. That added weight drains the battery faster. This means ferrite is mostly limited to cost-sensitive micromobility, like electric scooters, where extreme power-to-weight ratios are not as critical. For larger vehicles, the industry is looking at a premium alternative, iron-nitride magnets. This approach is being developed by Niron Magnetics and has secured heavy backing from GM and Stellantis. Iron-nitride magnets allow legacy automakers to eliminate rare earths while keeping their existing factory tooling and motor designs exactly the same. Material swaps solve the geopolitical bottleneck, but they create a new dilemma. OEMs must either sacrifice vehicle range by using ferrite today, or wait for unproven iron-nitride facilities to reach mass production scale in the future. The second pathway involves changing the motor architecture. BMW is a leader here, using externally excited synchronous motors in premium vehicles like the iX. Instead of using permanent magnets, BMW uses electromagnetism. They achieve over 95% efficiency and strong highway performance by using physical brushes and slip rings to deliver electrical current directly to the rotor. However, those mechanical contacts create friction and electrical noise. Because brushes eventually wear down, these motors introduce long-term physical maintenance requirements that permanent magnet motors avoid. Other developers remove the brushes entirely. Chara Technologies builds synchronous reluctance motors, which generate torque using carefully engineered steel geometries instead of magnetic pole. Chara states their design delivers a 15 to 20% cost advantage at scale, alongside a 15 to 20% higher driving range compared to standard rare earth motors. The hidden cost of this architecture is its extreme mathematical complexity. Reluctance physics are highly nonlinear. To prevent severe vibration, automakers have to develop proprietary software algorithms to manage the drivetrain in real time. Mechanical architectures can match the performance of rare earths, but only by introducing physical friction into the hardware or extreme algorithmic complexity into the controller. The third path is the software-defined motor. Companies like Vimag Labs, Valeo, and ZF are engineering drive units that eliminate both the physical magnets and the mechanical brushes. Vimag's core innovation is on the rotor. They use a patented rotating transformer to wirelessly transfer electrical power to a set of standard copper coils. Because there are no physical magnets to melt under extreme heat, the risk of permanent thermal demagnetization is removed. Engineers can run these motors at higher temperatures, using simpler, lighter cooling systems. Controlling that wireless power transfer requires moving away from standard deterministic math. Vimag replaces those physical equations with machine learning and regression models that recalculate the magnetic field 20,000 times a second. Running those calculations creates a hardware conflict. Standard automotive microcontrollers are optimized for permanent magnets, and they waste computing power trying to run these specific regression models. To fix this, Vimag is developing proprietary silicon. By building an application-specific integrated circuit, or ASIC, they estimate they can slash the bill of materials for their control electronics by 90%. This reveals the strategic trade-off. Automakers are successfully escaping a rare earth mineral bottleneck, but they are trading it for a global semiconductor bottleneck. On the factory floor, however, the upside is immediate. Manufacturers like Gendamark are using a modular Lego model approach to assemble Vimag's unmagnetized rotors. Automated factories prefer this approach because robotic arms no longer have to fight violent magnetic forces during assembly. The copper and steel carry zero magnetic charge until they are electrically energized, which lowers scrap rates and defects. Software-defined motors unlock thermal resilience and easier automation, but getting them to market requires significantly longer software integration times and relies entirely on securing a custom silicon pipeline. There is no universal winner in this race. As this decision tree shows, the most viable technology depends entirely on an automaker's packaging constraints and their R&D budget. If we follow the first branch for micromobility and cost-obsessed manufacturers building 2- and 3-wheelers, Ferrite and Synchronous reluctance are the immediate, deployable solutions. These companies are trading physical weight and motor size for better cost efficiency and supply chain stability. Following the center branch, we find legacy automakers trying to avoid billion-dollar factory redesigns. Iron-nitride provides a direct material swap, allowing these companies to bypass rare earths while keeping their existing motor designs and factory lines intact. The third branch covers high-power, next-gen EVs, reaching 350 kilowatts and above. Software-defined motors provide the thermal headroom needed for those speeds, though success depends entirely on the stability of the semiconductor pipeline. The global EV supply chain is trading one set of physical constraints for another. Competitive advantage now rests on the ability to combine raw copper and steel with custom silicon and high-speed algorithms.